All right, this is our last objective from section 6.7. We are looking at spherical coordinates. Okay, spherical coordinates is going to be another system that's not just an extension of another coordinate system that we have, but a brand new system in 3 dimensions that only works in 3 dimensions. So we're going to need to introduce a couple of Greek letters um, that we're going to use for this system. So our first Greek letter is rho. Rho looks like a P, but it's a Greek letter for R, and it's pronounced rho. And if you write your rows like your P's, try to change the way you write your rho so that it looks different from a regular P. The theta is going to be the same theta as we've seen, and it's going to be an angle that's described in polar coordinates. And now that we've studied cylindrical coordinates, you can just say it's the same as cylindrical coordinates as well. And then that last Greek letter is going to be another angle, and this angle is phi. And it's going to be an angle formed by a positive z-axis and the line segment from 0 to that point. So I guess I didn't talk about rho yet, but rho is the radial distance. Let me say that again. Rho is the 3-dimensional radial distance from the origin to the point that you're describing. So instead of the 2-dimensional radial distance that we measured in polar coordinates, this is a 3-dimensional radial distance. All right. So now we want to tie this in with the things that we're dealing with. Well, if rho is going to be the distance from the origin to some point x, y, z, then that distance is going to be like the distance of the vector. So you can say rho is equal to the square root of x squared plus y squared plus z squared. We generally want rho to be positive, but sometimes it does become negative. So, and just to keep from messing around with too many things, we can take the square, or you can square both sides. So you'll have rho squared is equal to x squared plus y squared plus z squared. So this is a more common representation of rho in terms of our rectangular coordinate system x, y, and z. Now our theta is still going to be the same, and our theta was based on the angles. So our theta is going to be the tangent of theta is going to be y over x. We also had this expression where we had x is equal to r cosine of theta, and then y is equal to r sine theta. So I know it's cylindrical, but our new spherical coordinate system doesn't have an r. So if we can find a representation for theta, maybe we can fix that. So what we're going to do is we're going to take a look at this triangle in a slightly different, from a slightly different point of view. Okay, let's see. Let's look at this triangle flat and identify the different parts of this triangle. So this is the angle, the 90-degree angle down here. Now theta is down here, but according to the cylindrical coordinates, this distance here is like the base of that triangle, and that happens to be r. And this is rho. Now the tricky part here is that phi is the angle from the positive z-axis. So this is phi over here. Okay, but with some trigonometry and geometry, it turns out that this is also phi. This is the angle phi. So I want to know what r is. So I can replace this r here and this r here, and then if I can replace that r with respect to this phi and row, the phi in the row, then I can replace r with something with a phi in a row, and then I can have my system in terms of rho, phi, and theta. So what is r equal to? If this is my angle, and this r is the opposite side, and then the rho is the hypotenuse. So opposite of hypotenuse is sine. So I think sine phi is going to be the opposite side over the hypotenuse side. So that's r over rho. That means r is equal to rho sine phi. Okay, that's great, because now if r is equal to rho sine phi, then this x is going to equal to rho sine phi cosine theta. And then similarly, y will equal to rho sine phi sine theta. So now we have two of the equations that make that relationship between rho and phi and theta, and then x, y, and z. Oh, but we don't have z yet. So what is z? Z is this distance over here, the vertical distance. This is z. So now using the same angle phi, I can have an adjacent side over the hypotenuse. So with that relation, I can write the cosine of phi. Cosine of phi is equal to adjacent, that's z over hypotenuse, that's rho. So if I solve for z, I will get z is equal to rho cosine phi. So these three equations will be my transformation into spherical coordinates. So we also have this equation, and then we can use this equation as well, and then we can find z in terms of x, y, and z, and instead of working that out, I'll just show you the formulas. Okay, so the conversion between spherical coordinates and Cartesian coordinates, this here would be the most important set of equations you'll want to remember for spherical coordinates. And then I did mention these two, and then now if you want to find the phi is going to be the arc cosine of this. We could have gotten that by doing the arc cosine relationship over here and then solving for phi, but no big deal. But now that we know Cartesian coordinates and spherical coordinates, and we also know about cylindrical coordinates, here are another set of equations that relate cylindrical coordinates with your spherical coordinates. Okay, and I think you can derive that because here you're just looking for r in terms of phi and theta without the z or without the x, y's, and z's and stuff. So you can look at those relationships. Let's do some problems. The first problem here is asking us to find the rectangular coordinates of the spherical coordinates that are given. And so if I'm given the spherical coordinates, they're an ordered triple. And the first number is rho, the second number is theta, and then the third number is phi. So rho, theta, and phi make up your spherical coordinates, and they're saying these are in spherical coordinates. Let's find out what they are in rectangular coordinates. So to put this in rectangular coordinates, we'll use these set of equations, and then I can just easily get x by just plugging in the rho, phi, and theta. So rho is equal to 1. We have the sine of phi. Phi is pi over 6. This is phi. So that's sine pi over 6, but it's also the theta is also pi over 6. And so sine of pi over 6 is 1/2. This is root 3 over 2. So 1/2 root 3 over 2 and 1. So then x is going to be equal to root 3 over 4. All right. So we'll get our y. y is equal to 1, and then now we have sine phi sine theta. That's sine pi over 6 sine pi over 6. So pi over 6, sine pi over 6 is 1/2. 1/2 times 1/2 is 1/4. And that's your y. And then your z is going to be rho times cosine of phi. And phi is this last number, so that's pi over 6. And that happens to be root 3 over 2. And so now we have the point root 3 over 4, 1/4, root 3 over 2. Okay, so that's your rectangular coordinates. In our next problem, we are finding the spherical coordinates for these points, or for this point over here in rectangular coordinates. So in this particular problem, we have x, y, and z, x, y, and z, and then we can use the second set of equations in this box right here. So rho squared is going to be -1 squared plus 2 squared plus 1 squared. So that is going to give us 4, 5, 6. So we can say that rho is equal to root 6. Okay. Now the tangent of theta is equal to y over x. So let's write tan theta is equal to y. That's 2 over x. That's -1. So theta will equal to arctan of -2. Now I'll just leave it like that. You can probably punch that into the calculator to get some decimal approximation value, but I'll leave it like that. And then the last one is to find out phi, and phi is the arc cosine of that. So phi equals to arc cosine of z. Z is 1. And then the square root of this, so this is essentially rho. So we got rho to be root 6. So I don't think there's a nice formula for that, so I'll leave it like that. Then your spherical coordinates transformation will give us root 6 arc tan of -2, and then arc cosine of 1 over root 6. Okay, you can find decimal approximations by just punching that in your calculators. Okay, let's take a look at our next set of questions, which is to translate the equation back into rectangular coordinates and then try to identify the surfaces. So remember, these are surfaces that we're describing with these equations. All right, let's do the first one. The first one, we have rho is equal to that. I think we can do with rho, but if we square it, it might even be better. So let's do that little trick where we square both sides. So we'll get rho squared is equal to 9, and then the rho is equal to x squared plus y squared plus z squared is equal to 3 squared. So this is a sphere centered around the origin with radius 3. Okay, so that's that surface. Let's do the next one. The next one we have phi is equal to that. Oh, what is phi equal to? Phi is equal to the arc cosine of this thing. So let's see. So phi Let's change this to the arc cosine of z divided by square root of x squared plus y squared plus z squared. So that's what phi is equal to, and this is supposed to equal to pi over 3. Well, let's peel this through and see if we can get something out of this. Let's take the cosine of both sides. So we have z is equal to the square root of x squared plus y squared plus z squared is equal to the cosine of pi over 3. And I believe the cosine of pi over 3 is 1/2. So let's just call this 1/2. And then let's get z alone by multiplying both sides by the square root of x squared plus y squared plus z squared. And then if we square both sides, we're going to get z squared is equal to 1/2. Actually, we're squaring it, so that's 1/4, and then x squared plus y squared plus z squared. I suppose we can continue working on this. Let's take the, what can we do? We can multiply this by 4, or we can just subtract. Let's see. 1/4 x squared plus 1/4 y squared plus 1/4 z squared is equal to z squared. So let's subtract that over. Well, let's do it in the next step. So if we subtract this, this is going to become a positive. Actually, let's bring this over to this side. We get a 1/4, or let's write it like this: x squared over 4 plus y squared over 4 is equal to, and then on the other side, it'll become 3/4, right? 3/4 z squared. Now, I don't know if you remember, but when we have all the x, y's, and z's are all being squared, and they're positive on one side, positive on the other side, and there are no other constants around, you actually get a cone. So this is actually a cone. So let's multiply everything by 4 and divide it by 3. So it'll be x squared over 3 plus y squared over 3 is equal to z squared. So this here is a cone. It's not a perfectly diagonal cone. I guess it's not a cone. The angle of this cone is not 45 degrees, but as a matter of fact, the angle of that cone is actually pi over 3. So this is a cone that's opened up with an angle of pi over 3 from the positive z-axis. So that's what that is. Okay. All right, let's do one more, and we have this cosine. I think we saw this trick before with cylindrical coordinates, and what we can do for something like this is multiply both sides by rho. So if we multiply both sides by rho, I'm going to squeeze in the rho between the 2 and the cosine, and then I'm going to get rho squared is equal to 2 times rho cosine phi, and I believe rho cosine phi is z, and this is the whole x squared plus y squared plus z squared business. So this is equal to 2z. So I think what we can do here is bring the 2z over to the other side, x squared plus y squared plus z squared minus 2z, and then complete the square, because by completing the square we're going to actually find a new center. So half of 2 is 1, 1 squared is 1, so let's add 1 to both sides, and then we will get x squared plus y squared plus parentheses z minus 1 quantity squared is equal to 1. So it looks like we're going to have a sphere of radius 1 that has a center at 1, 0. So here is the point 0, 0, 1. I'm sorry, I didn't mean to say 1, 0. I meant to say the point 0, 0, 1. So that's your sphere, that's your center, and it has radius 1, so it barely touches the origin. Barely. It touches the origin. Okay, so that's your sphere. Okay, so I hope that helps. These cones and these spheres will become important for us later on. I mean, it's important to know now, but even more so when we start dealing with a special type of integrals called triple integrals. So that's a little looking forward to the future in chapter 5. All right, I hope this helps, and good luck.